Thanks for the introduction. Yeah, so I'll sort of like be a bit more quantitative than the previous presentations. I'll sort of like to introduce a technique which is called Bayesian methodology and how that fits into building criminal models for either predictive policing or risk assessment tools. And I'll show this on examples from the work that we do, right? So warning, there is some maths in the slides. I'll definitely, given the limited time, skip through them. And this is obviously not the ultimate solution, but it's building towards a better understanding of how mathematical models kind of could be used for crime, right? So a bit of background on really how the models are built, right? You essentially start with a set of input characteristics of data about the problem that you're interested in. You build a model, right? A mathematical model that represents this, and then this model allows you to do two things: prediction and inference, which is understanding the phenomena that you're studying. Now, in the end, decision makers are using the outputs of these models to be able to make decisions, right? For the maths that I'll have in the slides, I denote all the input characteristics as x. Theta are the parameters of the model. So, for example, how much is unemployment related to crime? And then y is the output, our predictions in terms of whatever we are measuring. So, in a real example of predictive policing, for example, our input characteristics might be characteristics of the environment, of demographics of the population, and we are trying to build a crime intensity model that tells us where there's probably more crime happening. The sort of like inference and prediction is estimating what are the risk and protective factors for certain types of the population, and what is the estimated or predicted crime rate. And obviously the decisions, for example, could be where do you allocate resources. So what I'm trying to introduce today is the idea of being fully probabilistic. So most of the time people are familiar with building models. So for example, here we have a deterministic setting where we have a ground truth, which is a function, this green function that we're trying to observe. We can understand this as maybe, crime rate. And you have noisy data, which are observations of this crime rate at different locations, but it's not the actual true function. So you come up with a sort of like model. So for example, a polynomial curve, right? You're trying to predict y, and you have different parameters theta of the model, and you optimize and come up with a single line that represents your expected, your best fit, right? And this is what it's used in regression setting and classification as well. But if you're fully probabilistic, then what you end up recovering is an uncertainty around your estimate. So you can see how we've introduced this shaded area here, which is the uncertainty around your prediction that captures how certain you are about what your model is, really, and the inherent noise and stochasticity in the data. Now, you go from finding one model that is suitable. As you see here, we're finding the model that minimizes the error or the accuracy, in whatever way you want to measure it. And we go from that to a framework where you have a probability distributions over models, right? So there's a whole bunch of models that could explain what is happening, and you derive a probability distribution for the models given the data, and you also derive a probability distribution for your predictions given the data. So you're not just predicting what the, for example, crime rate will be tomorrow, but you have a probability distribution around that. You have bounds for your prediction, and that is very, very important. I always tell my students, so I'm a lecturer in data science, and I always tell my students that it's better to be imprecisely correct than precisely wrong, okay? So quantification of uncertainty is really, really important, especially when you're making decisions on the models. So this is an example of how probabilistic regression works. So basically you have like a goal function that you're optimizing, and see we're trying to fit this function with the data, and we could go from everything from underfitting with a straight line to overfitting the data and really not representing what the best model is, whereas when you, in this case, are maximizing a particular quantity, you end up with a pretty good estimation of the function. And the best thing is that you have these bounds, the gray area, that represent how sure you are of the value of the function at all these different locations. Now, this comes really from kind of the fundamental theorem called, from Thomas Bayes' Bayes theorem, right? So the idea is that we are trying to find a posterior distribution, right, of the parameters theta, all the possible models. We want to understand what models are more likely than others, given the data. So that's called a posterior distribution. And this is actually proportional to likelihood. So the likelihood is the probability that the data is generated from a particular model and the prior, right? A prior is an estimate of what models are more likely to be suitable for the kind of analysis. Now, this is really crucial because this brings the expertise of the main expert. So it's not just the data speaking by itself, but it's actually reflecting the prior knowledge and criminological theory by introducing prior models that are more probable than others, and then combining that with the likelihood of the data to estimate the posterior distribution. Now, in the end, this becomes equal when you have a normalizing constant there, but I won't really talk more about that. The idea, in the end, is that you get a distribution over models based on prior knowledge and data. Now, this not only allows you to find a probability distribution over models, but also of a predictive distribution. So when you are predicting something, you also have a probability distribution around that. And that is done by summing up over all possible models. This in the Bayesian setting is called integrating out over possible models or marginalizing out all the possible models, right? In a perfect scenario, you have an infinite number of models that can explain what is happening, and the idea is that you take all of them into account and weight them depending on the probability that they are correct or not. So taking these sort of like background to particularly, you know, how do we build predictive policing models, or how do we understand crime? You know, what are the key drivers in terms of demographics, or, you know, characteristics of the environment, or, you know, what determines where there's more density of crimes or not on a Bayesian setting. There's actually been a lot of work in this area, right? So I might not spend so much time here, but there's a lot of just spatial models that are built to understand crime. There's a lot of models that just look at time series and models that combine this. So Predpol, for example, has you know, the self-exciting nature of understanding, you know, criminal models. And then you have HunchLab that is also using, that's from Philadelphia, they're also using some risk terrain modeling and other risk factors. And the idea is that we're also trying to sit there in the middle, which is combining all possible factors to be able to see and uncover what are the patterns underlying in there. So the information sources for the case study that I'll show you today is historical crime records at New South Wales in Australia, which is one of the biggest states where Sydney is. And we have historical space-time criminal records, so pretty much where each crime happened. And we're also combining that with all the demographic information that we have across Australia. There's actually 8,000 of these variables. Some of them, as you can see, you know, pretty much we included everything: population, density, education, marital status, indigenosity, etc., etc. And the idea is to build a probabilistic model that it's able to do the two things that I mentioned, right? One thing is prediction, and the other thing is inference. So understanding what are these factors that could be sort of like related to crime. So how do we do that? Well, we start by, you know, discretizing the environment. In this case, we have postcodes in Australia, which are sort of like a couple of blocks big. And for each one of these, we have all the bounds and all the kind of geographic information for them. And we've collaborated with police, New South Wales Police Force, who give us all the data about all the crimes, the number of assaults, the number of robberies, the number of motor vehicle thefts, and we can kind of include all the number of crimes in each one of these locations. Now, the idea is that for each one of these geographical units, we also have a lot of explanatory variables. So hopefully you will have much more in the future, but, you know, at the moment we had, as I said, 8,000, and we're picking a subset from this. We're putting a prior over the models based on, you know, domain expertise. So theoretical, you know, studies and experts in criminology are suggesting what are the variables that are more related to a certain type of crimes. Now, we actually found that these are not really fixed, but it depends on what model you're building. So then we kind of build a huge database, right, that has, for each one of these areas, it has the geographical coordinates that we define here as U. We have all the demographics or environment characteristics, location-specific characteristics X, and we have the number of crimes that happen in that area as Y. Now, the idea is to be able to use U and X to understand Y, and we do this in a Bayesian setting. So I might really go very quickly through these slides because they contain sort of like the core maths that we're building in terms of the algorithm. So Y, as I said, is what we're trying to predict, which is the crime rate at the location. X are all the location-specific characteristics, which in this case are demographics, and we assume a sort of like linear model in that sense. It's actually a bit more complicated, but I don't want to get into details. Then we also have a spatial kind of automatic correlation that the machine learning algorithm learns, right? So how are areas that are close by related? And some inherent noise in the process, obviously, because we cannot fully predict what's going to happen. Now, the cool thing is that by using a Bayesian methodology, we can learn the parameters of this model, right? So the parameters are this model pretty much could be used for predicting influenza. I've also used it on my PhD thesis for understanding pollution. But here, right, we are trying to see how this could be used to understand crime. And these parameters here need to be adapted based on the data that we have. So it actually can provide an infinite number of models depending on all the parameters, all the different value or combination of parameters that you can set. So the challenge is, how do we learn this set theta of parameters that defines how our models is building their predictions? So in order to learn this model is where machine learning or artificial intelligence come, right? So one thing is the statistical modeling, and then machine learning allows you to learn from the data these models. So we have the data, which is all the X, all the characteristics, and all the Y's, which are the crime rates, and we make use of Bayes' theorem to find this probability distribution over the posterior, right? And that had been actually impossible until the recent decade, where the rise of sort of like computing power and the possibility of evaluating a large number of models was available with algorithms like Markov chain Monte Carlo, right? So with this algorithm, we're basically generating samples, right, from models. So remember, theta were the parameters of a model. This iterative algorithm allows you at every time to sample a different model from an infinite number of models, and you see how likely this model is to generate the data by evaluating the likelihoods, and then you repeat this over and over and over and over again. Now, there's several theoretical guarantees that tell you that in the end, the distribution of models that you are sampling will converge to the actual true underlying distribution of what models are more likely than others to generate the data. So in the end, we approximate these complex distributions. The first one here allows you to predict what is the probability of a crime at a new area that you haven't observed given the data. And these are the marginal probabilities of each one of the factors that you are considering. Now, these are very complex sort of like integrals that you couldn't evaluate until recently, where you can run these kind of algorithms and you can approximate these complex integrals by the chains of samples that you're getting from these algorithms. So I know this might be, very sort of like complex, but the overall idea is that we are considering the space over all possible models to build our predictions and our inference. Now, what does this look up really? So we sort of like validated our model in New South Wales. So we have all these different regions where we have the crime rate, and we have all the characteristics of these regions, and we've evaluated how the model behaves by leaving out some of the data, right? So we have sort of like hide some of these regions, actually around 25% of the regions, to the algorithm, and we've used 75% of the data to sort of like supervise, or in a sense provide some data for the algorithm to learn what the most likely models are. And then it comes up with predictions, which are here highlighted. So you can see on the x-axis in this figure, you have observed crime rate, where each point is a different region in the map. And the y-axis is the predicted crime rate at these locations. If the algorithm would be perfect, you would see all this lying in a perfect straight line where our predictions match exactly what the observations are. The good thing is that we are sort of like pretty close in a sense that high crime regions are predicted to be high crime rate as well. So I'm running a bit short on time, so I'll really sort of like go a bit faster. But this is sort of like what the output of the model is in terms of the factors that we've considered. This is just a subset of them. So we have population density, person identified employment, and how these are related particularly to domestic violence over different years. And the algorithm come out, we could be sort of like discussing, you know, these factors, how likely they are to be related. And here we are not really building a fully causal model. But you know, there's a lot of discussion that could go around about these factors, but it brings up some interesting patterns about, you know, how unemployment or financial stress in general, population density are related to domestic violence, and we find different patterns for different crime types like burglary or motor vehicle theft. Now, how can we use these models to make decisions, right? Is also using a Bayesian setting, right? So we're not just building models now that are based on our expected crime rate, but we are quantifying the uncertainty around these models. So we suggest that decisions cannot be just based on an expected value, but they need to be based on a probability distribution. And how do you do that? Well, that's what Bayesian optimization is for. I'll quickly run through this algorithm as well. So you have this unknown function, which is crime rate, right? If you have a lot of data, you plug all this data, you build your model. But if you're incrementally getting data in the, you know, with decisions that police are taking, for example, of deciding where to patrol, then this algorithm allows you to do things, two things at the same time. One is reducing the uncertainty. So the uncertainty in that plot there is the shaded area, the purple area. And what you're trying to do is you're essentially evaluating a function that tells you where do you have to sample next. So you see how we include this new observation of the function, and the uncertainty around our prediction shrinks because we have a new observation of the crime rate. So, but then there's still all this area that has a lot of uncertainty. Now the next point that picks is up down there. So in the end, right, the algorithm would allow you to reduce the uncertainty, but also explore the areas that have higher crime rate. So we are using this model to be able to build patrolling routes that are hopefully going to reduce bias because the algorithm will explore and will exploit at the same time. So usually when police want to go and patrol, right, and I've seen this, you know, in first hand by working with them, is they still put pins on maps and go to the areas where they think there's going to be more crime. They don't really assess uncertainty in a proper way. So we were trying to propose is that if you're not sure really what the crime rate is in an area because you don't spend much time there, well, you should actually go there to make sure that you know what the crime rate is in that particular region. This could also be used for prediction instruments, and really here I'll sort of like very quickly skip to the important slide because we're working with New South Wales Justice Department and well as this, and we're using data from juveniles that are already being assessed by risk with a very rudimentary form of 6 questions that they have to answer, and then they are evaluated in terms of the risk. We're trying to build a fully Bayesian model that allows us to consider all the information stored for each one of these individuals. Now, why is this important? Because, in a sense, risk assessment is already being done, and it's not being done in the best way at all, right? So they're assuming that all the individuals are sort of like all the factors they're measuring are the same across all individuals when they're not. And they're also kind of assuming that the risk is static when it's not, and you know there's a lot of sort of like bias in the system anyways. So we were trying to do is really like, and sort of like we've discussed, what would be the perfect scenario for you? Well, they always say, if I had a limited number of time to go through every record of each individual and, you know, go through all their history in terms of previous convictions and whatnot, I would potentially, you know, an expert would evaluate what the risk is. But in a perfect scenario, they have limited resources, they have this form of 6 questions, and they're not really doing anything complex. So we want to be more efficient and introduce these methods to be able to predict risk, right? So again, we're trying to use all this information across times for individuals, right? How many incidents they have while in detention, misbehaviors, pre-classifications that have been done in the past, orders, detention orders, and so on. Build a mathematical model where we're plugging all of these, and again, find the distribution of models to be able to predict risk. Now, I just want to end up with this slide. So how does logistic regression is something that you might be aware is being used for predictive risk assessment tools all the time. So you might be familiar with this, you know, concept of 0, low risk, 1, high risk. We have a lot of people, like, you know, that we get scores for between 0 and 1. and then we put a threshold, right? So this is the output of logistic regression, and basically tells you everyone who is above the threshold should go on parole, above the threshold should go out on parole, and the red should stay in jail, basically, for example, right? But that is assuming that you know the point estimates. You're not quantifying uncertainty in this model. Now, if you quantify uncertainty, then for this individual, that would be high risk according to the threshold that you've set, if you consider a probability distribution around this estimate, so for example, this is one probability distribution, if you consider this uncertainty, you might decide, yeah, well, this actually, kind of this person is, for any model, for most of the models that we use to explain his future risk, then he is above the threshold, so we might make a decision. But for that same individual, a different model would tell you that his risk or probability distribution of his risk looks like that, where he's likely to be above and below the threshold at the same time. So now, even though you have the same expected value, you have uncertainty around that predicted probability, and therefore, if you take into account this uncertainty, now it's not very easy to make a decision on this individual. And this might be able to drive the decision, the information acquisition process, to be able to narrow down the uncertainty around the estimation for that individual. So the future work that I'm working on is try to incorporate causal inference using dynamic Bayesian networks. I'm also trying to incorporate information from the environment using computer vision to automatically extract features and conduct randomized control trials for the decision-making algorithms and help police make unbiased sort of like decisions. That's the presentation for today.
Thanks, Rahmen. We have time for a few questions, and the cube is there, at the back there. Sorry, you, the person looking back, you. Yes. Sorry, I don't know your name, so I'm just.
I'm Michele Eloy. I am a philosopher. So let me see if I got if I can translate it in my own terms. So I'm thinking about starting with Harcourt's problem of what he calls the self-confirming prophecy. It basically says that when you have these predictive systems in criminology, you end up basically sampling from the populations which you consider to be high risk, and that causes what he calls this ratchet effect, that then eventually it's an objection for him. From what I understand, this kind of model would kind of avoid that criticism, because being Bayesian, so to say, it attaches a higher value to information that would be highly unexpected given the dominant models, the models that are already assumed given the prior. And so basically it will unlike the models that Harcourt criticizes, it will actually direct police to make checks in a way that will not confirm the priors, in a way that actually it will attach more value to information that it will be surprising given the priors, given what we have been doing in the past. Is that more or less the idea?
Yeah, that's exactly right. So we've actually thought about, how decisions are being made by police and how we can reduce this existing bias of over-policing of certain population. And by quantifying the uncertainty that you have around the population that you're not over-policing, and building that into the reward of the overall decision-making process, you end up reducing exactly this gap. So it's exactly fine. You sort of like understand the idea around Bayesian optimization is to pursue the exploitation, so how much you know based on the data that you have, but at the same time balance that with exploration, which is reduce your uncertainty about what you don't know.
Yes.
Two questions, please. Once the algorithm is ready, the one that you're actually using, can you then tell the weight? I think you called it the theta. Can you tell the weight of each factor in the algorithm? So that's one technical question. The other one, is there a limit to how many factors you can put in? I think it was the X, like you can
Very good question.
Just be endless? And if there's no limits, why not use anything?
Yep. Okay, so the answer to the first question is yes, you can find the values of the parameters in a sense, right? So these are the values, so each one of these plots shows the value of the thetas for the relation between the demographics that we've used, so the input characteristics basically to the model, and the output, right? So, so for example, the number of males separated is the highest sort of like explanatory variable for domestic violence that the model came up with. Population density also seems to affect, and unemployment. Now you can see that these are all sort of like boxes, so some of these are larger than others. That's because we are quantifying the uncertainty around the value of that parameter. So you might not be sure of the exact value. In fact, you can never be sure of the exact value of, you know, how employment is related to crime, but you have an idea of how important it is. So yes, you can get the betas, and regarding the second question on the number of parameters, that's a very sort of like broad area of research in general, because the number of models grows up exponentially with the number of characteristics, right? To like 2 to the power of the number of characteristics that you're trying to build is the possible number of models. So for example, if you have 1,000 characteristics, that is already 2 to the power of 1,000, which is more atoms than in the entire universe. Okay, so you basically cannot really explore a universe of this size, but there's techniques that could allow you to approximate in this enormous space, and we're trying to explore that and making that efficient, but it's an active area of research. So essentially, we are using around 20 variables. We could go all the way to 50, but then when you go to 100 and even more, it becomes untractable, but we're trying to work on that.
Yeah, I just have a quick question about your timeline. Like, when were you thinking that this can actually be deployed with the criminal justice authorities? Are some parts of what you showed us actually being deployed by the law enforcement or courts? And when do you think would it be in practice in Australia?
So they've give us data. We've run the models and sort of like we've showed this back to police, but between that and really being able to do a randomized control trial on are these patrols less biased or are these patrols, you know, providing better outcomes, I think we're at least a year or 2 away from that.
That's not a lot.
Yeah, it's not a lot, hopefully, but I'm also in touch with other states at Australia. So for example, when I go back now, I have a chat with a Queensland police force that they're also willing to participate as well and provide access to the data. So it's very good that they're kind of willing to participate and understand what it's potentially, you know, biasing and over-policing.
Yeah, okay, I try to make it short. Am I right that actually this kind of predictive model only works in a penal theory or concept which believes that deterrence or harsh sanctions avoid new offenses, or the other way around, is the model taking into account what a harsher sanction, which would be the outcome of being predicted to be a high-risk offender, actually does to the probability in the future to commit a crime again? I mean, isn't it not just postponing the new and even make it worse by letting the guys, I mean, looking at recidivism studies, which have a kind of general finding that the longer the life sentence, or the longer the sentence or the sanction, then the more the probability rises to commit a new crime?
Yeah, good question. I don't have a clear answer for that, obviously. I think we need to be able to evaluate what the outcomes are, what the interaction between different sentences or between policies and the outcome of these policies. So having an understanding of that is obviously crucial to answer the kind of question that you have, and we haven't conducted that analysis yet, right? So one of the things that we're looking at to be able to understand that in risk assessment tools is in this slide where I've showed that we have all the information from young individuals over time. What we want to do is to be able to include here programs or the actual risk they had and reinforce that in the system to understand what programs provide better sort of like outcomes in the future. So part of your reward is, to minimize the risk, and your decisions are the programs or the sentences, and understanding that dynamic that will depend on individuals as well. So different individuals might be reluctant, might have different treatment effects, and understanding that is one of the challenges. So usually modeling aspects treat all individuals the same, but we believe that that is not necessarily true.
Okay, we've got time for two very quick ones, I think. Mark.
Okay. I was going to squeeze two in. Should I do?
Oh, no, you've got one.
I've got one. Thanks so much for that presentation. You must be an amazing stats teacher because you were so great at making quite complex stuff clear. One question, maybe I missed this, but is there a way that this model can take longitudinal effects into account? And I just wasn't sure on how the data worked in terms of what time frame it was collected. So when you have all of the variables that you use as factors, is that, I don't know, census data or over a particular time? And then do you correlate that with the number of crimes during that time period? But is there a way to look at historical effects and see how those transform the model over time?
Excellent. Yeah, I didn't have really much time to describe this, but so we've used crime data from 1995 till 2016, so 20 years worth of crime data, and we've sort of like divided the analysis, a cross-sectional approach, where we've used demographic variable from the demographic information from the census at different steps every 5 years, right? So we build, that's why we have like the effect here, for example, for 3 different census years, right, for 2001, 2006, and 2011. And we're currently building, generalizing a bit more this model to include the dynamics of time. So, for example, include, right, time dependency directly in the model so you can extrapolate your predictions. Yeah, I guess the short answer is we're working on incorporating the time dependence directly in the model and not just building a cross-sectional. And one last one here.
Yes, a very quick word. I was prosecutor in France during 3 years, so I used to fight against crime. And when it comes to, how can I say that, send police in a place, I'm pretty sure that if I send a policeman in a place, he finds something. You know my point. It's a kind of performative effect. So by predicting things, for sure you reveal maybe other things. So I don't want to discuss here, of course, about Bayesian versus frequentist approach, etc. My just only question is that when I read that thing, I'm sure that someone poor who lives in a poor region, who has no education, maybe is more supposed to commit a crime, just because in cultural environment all around here, it can have that kind of effects and bad effects. So as a policymaker, what I want to do is maybe invest more in education, etc. So brilliant work, really. It's tremendous for me, and again, it learns me things about Bayesian approach about that. But what is new with the other things we already know about committing crimes, etc.? What is the added value for the work of persons which fights crime?
Right, I think, well, thanks for the comments and questions. So you have, with the Bayesian methodology, obviously you are sort of like confirming what the theory already says, right? You know that people in disadvantage on financial stress will likely commit more crimes, and the models are identifying those as sources. Now it tells you, at least it helps government in terms of decision making, how to efficiently spend the money to be able to tweak some of these levers to be able to reduce crime. That's what we're aiming with this. So eventually we can say, you know, for this new area that is being developed, or for this area that has a crime rate, the algorithm is estimating that if you reduce employment by this much, you'll be reducing crime by this much. But if you change education, you'll be reducing it this much over this long term. So it allows you to understand pretty much what the effect of the decisions that you're making are. And it'll hopefully be, you know, it'll hopefully help What I think it's new is that it will help to reduce existing bias. So the point that you say, you know, you put police, you'll find more crime. That is also something that we're trying to uncover and understand. But you will, even if you put police at different locations, they will still find more crime at one location than another. So there will still be a difference. So even though you send police, you will obviously find crime. On some areas, you'll find more than others. And that's something that we want to uncover.